always a little bit scary.
Most of it is pretty chill. It's like there's two problems left that are just painful. Because it does a lot of like deriving and stuff, rather than like plug in numbers for what we know.
Yeah.
I did have one question I was curious about for like the step length, stride length. Because we talked about how in theory they should be about double, but they're not in practice always going to be double. Like what do they consider like the acceptable range in terms of like percent difference you'd expect from like the double, that it's like there's nothing to be too concerned about?
It's a great question, actually. That I'm not 100% sure. Yeah, I'd have to make friends with them tonight and see. I don't know. Yeah, it's for most people, it's never quite exactly double, but it's very, very close. So within like 5%.
So, okay. So that means that because they can probably use that to tell if like something's off, that
Yeah.
like two or like, oh, this is not that close. to
Exactly,
this,
yeah.
So there's something off, whether it's like the length isn't quite right or the frequency.
Yeah.
Okay, cool. Yeah, I mean. Yeah. Yeah. Oh, yeah, just, I was on. So you end up with you went. It's just a winning. All over the US, there. I'm glad I glad. Regular. Yeah. You're seeing, right? That's. Oh, that's. I didn't. Yeah. What about the same? Yeah. I know, I want to guide you. Never responded. Okay. Always goes when you're.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, so I guess first obvious thing is I graded your midterm exam, so your grade is on Canvas. So I brought the exams for me today, so you guys can pick it up after class today. So the average was about 37 out of 50, so that's right about kind of, pretty typical of the first exam. So, you guys did fine. You guys did average, okay? Yeah, question.
Do you find that midterm super average is higher or lower than midterm?
Honestly, it depends on the person. Usually with the policy that I've adopted, so I've adopted this higher and lower midterm policy for the last couple of years. Usually it's like, if you do poorly on the first exam, you do better on the second exam. And, people who did really good on the first exam kind of take it easy on the second exam, and then they don't do so well on that one. But difficulty wise, I would say second midterm is maybe a little bit more difficult, just because it's, there's a bigger variety of equations that we're going to go over the next few weeks. Bigger variety of topics. It's not just kind of statics. But people kind of, it all kind of averages out in the end. Yeah. Yep. All right. So yeah, so I have them available to pick up today. Definitely check over the exams. At the very least, just make sure that the score that's on Canvas matches what's on your paper. So I've made a couple just mistakes like that in the past, so you want to make sure that is correct. And then, I've tried to leave as many comments as I could, throughout the exam, so make sure you kind of read those as well. Okay. All right, and so the topic for today, we're continuing on with our lecture from Monday. So we're continuing to talk about Gait biomechanics. So we started talking about walking on Monday, and today we're going to get to running after we kind of go through, finish up. We're going to finish up a few final things about walking, and then get to the running part. Okay. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. Okay, so on Monday, we left off with this idea that, walking is a very complicated phenomenon, right? It's not something that we really think about because it's just so natural to us. But walking, there's a lot involved with it, from the coordination of all your muscles to all the different things that you can quantify about it. It's complicated, right? And walking is not the only thing that's quite complicated about human motion. It turns out a lot of the things that we kind of take for granted, even just the simple thing of me just doing these. Oh, sorry. Even just the simple thing of just me doing this, Italian hand motion thing that I like to do, is very kind of complicated. So a lot of times, we kind of have to simplify things in order for us to better, in order for us to just better understand it or to just kind of better work with it, right? And that's kind of already true, for everything that we've covered in the class so far, right? And so, a lot of the static situations that we've looked at, we've kind of simplified it to kind of just look at a single muscle and a single, joint, right? But in reality, it's a lot more complicated. So, as we get into human motion, this idea of modeling and kind of simplifying a situation is going to be a lot more apparent. So I want to take a little bit of time today to talk about one of the more interesting models for walking, which is called the ballistic walking model. Okay. So the ballistic walking model is a simplified view or simplified, expression of the mechanics, the biomechanics of walking. Okay. And it kind of builds off this idea that we kind of ended the lecture with on Monday, that walking for the most part is actually fairly passive, and so it doesn't need actually a lot of energy input from the body. Okay. Kind of once you get the walking motion going and you have some forward momentum, really there's not that much energy that needs to be put into it. Really, the only energy that you're really exerting when you're walking is just the usual amount of energy that you need to support your weight, right? And so just the fact that you're standing on your feet and your muscles need to exert some energy or some force just to support your body weight. There's really not that big a difference between the amount of energy you're exerting walking versus just standing still. Okay? Okay. And so in fact, what we saw, when we looked at kind of the interchange between the kinetic energy of the body and the gravitational potential energy, was that there was a kind of a trade-off, right? And so I'm just going to scroll up here just for a second, just because I don't want to draw the graph again, right? And so this is kind of the graph that we ended with on Monday, where the kinetic energy and the potential energy kind of are both kind of sinusoidal looking waves, but they're kind of opposite of each other, where one is peaking, the other is down, and the other one's down, the other one's peaking. They kind of trade off like that, right? That looks very similar to a pendulum, right? And so the idea with the ballistic walking model is to take this idea or take kind of this inspiration and then kind of build a model out of that, okay? Okay. So there's quite a few forms of it. So I'll kind of draw you kind of the most simple form and kind of the one that looks a little bit more realistic. Okay. So the most simple form of this is it's just simply just an inverted pendulum. Okay. And so an inverted pendulum, if you've never seen one before, it basically just looks like a metronome. So it is a pendulum that kind of is upside down. Okay. And so this inverted pendulum will just kind of go swing back and forth. Okay. And this inverted pendulum, even though it looks really simple, this inverted pendulum almost pretty much mimics the motion of your stance leg, right? So when your foot is kind of in the ground and you're moving forward, right? If you kind of track the motion, or if you kind of imagine that the kind of the ball at the end of the pendulum here, this is your hip joint. Okay. And if you kind of watch someone take a step, right, their hip joint kind of makes this kind of, circular motion. Not quite as circular as an inverted pendulum, but quite similar. Okay. Okay. All right. And so that inverted pendulum kind of forms the basis for the ballistic walking model. Okay. And so the final form for the ballistic walking model basically takes this inverted pendulum and just adds the second leg to it. Okay. And so the ballistic walking model, again, you kind of have this inverted pendulum. Okay. Okay. And then what it does is that it adds the swing phase leg. Okay. And so your swing phase leg has, it's your knees typically bent. Okay. And then what you can do, so this is kind of at the end, right? And so if you kind of imagine that the person's walking this way, right? And so if you set the ballistic walking model off with just the right conditions, right? So if you set the mass here with the right position, with the right velocity, you can use this ballistic walking model to basically mimic the motion of a single step. Okay. And it's pretty good. And so if you ever get the chance, I would look up a video of a ballistic walking model, you'd be kind of amazed at just basically this is just like 3 sticks. And so if you have 3 sticks, you connect it together. Now granted, you have to make sure the mass is kind of centered well. But if you set it going with if you kind of push it with just the right accuracy, it really does kind of look like someone taking a step. Okay. All right. So this ballistic walking model can be used in a very interesting way. Okay, so obviously this is a very simplified model. It doesn't mimic all of the muscles that are there. In fact, it doesn't model any of the muscles. Okay, but we can extract some very interesting information from this. Okay, and so kind of focusing on the inverted pendulum. Okay. Let's use that model to compute, let's say maybe the theoretical maximum walking velocity of a person walking. Okay. Because remember, the thing with this inverted pendulum is that besides the initial condition, we're not inputting any additional energy, right? And so you're walking kind of as passively as possible. You're just kind of letting gravity just kind of do the work. Okay. And so if you're doing that, let me kind of draw this pendulum again. Right. So we know from what so we know just from pendulums in general, right? The maximum velocity is going to occur when, when this mass is at kind of the midpoint of the motion. Okay. And so if we said that this leg has a length L, this mass has a forward velocity V, okay? If we compute, so let's say that we compute the centripetal force. I always forget how to spell centripetal. Okay. And so the centripetal force for a pendulum or any just kind of any circular motion is mv squared divided by 2, or divided by L, excuse me. Okay. And for this inverted pendulum, the centripetal force, remember the centripetal force is the force, that kind of keeps this pendulum within a circular arc, right? And so the only force that's acting on this, if we're not exerting any of our muscle forces, the only force that's providing the centripetal force is gravity, okay? Right, and so with this relationship in this position right here, we have to have the relationship mv squared over L is equal to mg, which is the force of gravity. Okay. And so if we solve this expression for v, let's go ahead and cancel out m from both sides. Okay. I'm going to multiply L by both sides as well. So L is going to come over here. What we get from this expression here is that the maximum velocity is equal to L square root of L times G. Okay. Right. So what this is telling us is that, if you have longer legs, and you're walking at kind of a typical kind of cadence, right? And so you're not really exerting extra energy to jog or run or anything like that, then, people with longer legs have a faster walking velocity. Okay. So that makes sense. And so, I think that's kind of generally what we kind of our intuition tells us. Okay. If you have longer legs, you can just cover more ground with the particular step. But the other interesting thing here is that our maximum velocity also depends on gravity, right? So normally, for 99.99% of cases, that's kind of irrelevant just because, we're all here on Earth and we all experience the same gravity. But, for instance, if we were to kind of take, let's say that, in the distant future, we're able to kind of travel to different planets, or travel to the moon, travel to Mars, something like that. That means our maximum walking speed on those planets is going to be affected by gravity. Okay. So if you think about, there's a lot to be said about how, movies and video games and just media in general how they interpret science. But, if you think about, movies where people go to the moon, any kind of media where people, it's always shown that people are just walking really slowly, right? That's not just a Hollywood effect. That's just the fact that, the gravity is less on the moon. And so, the speed at which your foot can come down to the ground is going to be less. And so that's going to affect your walking speed as well. Okay. And so unless you kind of exert extra energy where you're kind of pushing your muscles to kind of propel yourself forward more, there's a limit to how quickly that you can walk through just purely passive means. And that can be approximated through this formula here. Okay. All right. Any questions on this? Okay. All right. And so this kind of little exercise here kind of highlights something that's really important about models. And so, a lot of times when you use a model, it's not going to be 100% accurate to the real life scenario. Okay. In reality, most people don't walk with an inverted pendulum. So a lot of times, people are exerting kind of extra forces in their muscles, either to walk faster, right? So a lot of times people are kind of in a hurry and they want to get from point A to point B faster. So they kind of do like a speed walk, so it's not 100% passive. But they also might want to walk slower too. And so, there's, maybe you want to take your time and take it easy, right? So a model like this isn't going to be 100% accurate to the real life situation, but models can still provide really interesting and really useful information as well. Okay. So think about all the problems that we did in the first half of the class, right? So basically all of those problems we did in the first half were models of reality, right? Because even if you have a static situation, you're going to have more than one muscle most of the time, kind of working on your to keeping your body in a particular position. Okay. Real life is 3 dimensions as well. So everything we did in the first half was 2D. So even though everything we did in the class, up to this point, you might make the argument that you could dismiss it where it's like, oh, it's just 2D or oh, it's just a single muscle. So, but we still learned a lot from doing all those problems in the first half. So a model doesn't have to be 100% correct to be useful. Now, if you're doing quantitative analysis where you're measuring, you need to have exact answers for some kind of analysis. Yeah, your model needs to be more accurate. But you can still gain a lot of useful insights. You can still gain a lot of useful information when a model is not 100% accurate, but maybe captures a certain part of your phenomenon well. Okay. So I want to make sure I kind of mention that just because human motion is complicated, and so we're going to be modeling it, often simplifying it to a great degree. But that doesn't mean that what we're doing is not useful or is not correct at all. It's just it's just simplified just so that we can kind of understand. Okay. Okay. All right. So let's go ahead and move on to the next topic. So next topic with walking is this idea of kinematics. Okay. So kinematics is something that we're going to spend quite a bit of time on just because, being able to describe motion is really important. Okay. So kinematics, if you kind of remember from your previous classes, kinematics is kind of the subject of just simply describing the motion. You can almost think of it as like the language of describing motion. Okay. Because if you're going to do any kind of science or any kind of analysis on a subject, you first kind of need to agree on what's the best way to describe it, right? Just like if you're going to communicate with someone else, you need to have kind of a prior agreed upon language in order to kind of talk with them, right? So kinematic is just that way for describing motion. Okay? And so, when you think of kinematics, before, even before coming to this class, most of the terms that you might be familiar with are things like position, things like velocity, acceleration. Okay. And of course, all of their angular counterparts as well. So angular position, angular velocity, angular acceleration, and so on, right? So these are all terms that we use to kind of describe something in motion, right? Okay, so for human motion, right? Most of the kinematics that we're going to use are angular kinematics. Okay. In particular, we're going to use the angular kinematics to describe the relative, orientation of two kind of adjoining limbs at a joint. Okay. So I think that's definitely kind of an adjustment for most people, because I think, for the most part, most people are kind of adjusted to kind of thinking about kinematics in terms of linear terms, right? So linear position, linear velocity, linear acceleration. Okay. But the way that kind of the human body works is that, the motion of one body segment, really kind of depends on the motion of the adjacent segment as well, right? So I can kind of move my hand kind of back and forth like this, right? My wrist joint may not be moving, but the position of my hand is moving because it's moving relative to my lower and upper arm. Okay. And so kind of the agreed upon standard to kind of the best way to describe this is to mainly go with, angular kinematics. Okay. So if you have a human right here, right? I don't know why he's making that pose, but it's just to kind of illustrate this, right? So if we want to describe this motion, we're going to be looking at, what's the angle of the elbow joint, right? What's the angle of the shoulder joint? Okay, knee joint, okay. Hip joint, right? So as a person goes through their motion, the angles between the angles at these joints are going to change. Okay. Now, of course, you can compute things like, where is the center of mass of the upper arm and how does that change as a function of time? But a lot of times, we compute something like that based on the angles. And so the angles are kind of the first things that we compute if that's the primary variable. And then based on what we measure from the joints, we use that information to compute other stuff. Okay. Okay. All right, so just to kind of give you an example, let me give you some sample graphs of what the kinematics of walking actually look like. Okay, so walking, very kind of general, very kind of simplified, at least speaking, walking heavily involves kind of three joints, and so it involves your hip joint, it involves your knee joint, and the ankle joint, right? Okay. And so if we were to track those joint angles, Now, of course, you know, some of these joints they can't just be described with a single angle. So the hip joint is kind of one example of this, right? The hip joint is a ball and socket joint, so you can't really just describe it with one angle. But, you know, when you're walking, you know, your hip joint is mostly just going through extension and flexion, right? You're not really abducting your knee outwards or adducting it inwards. There's a little bit of that motion, but for the most part, your knee is, you know, just extending forward and, or excuse me, flexing forward and kind of extending back, right? So what we can do is, you know, let's say that a person is, taking a walk and we observe their joint kinematics as a function of time. Right? All right, so for example, let's measure the hip flexion as a function of time, okay? All right, and so on the on the horizontal axis here, we have time, okay? So this is going to be over the course of a single gait cycle. And on the vertical axis, we're going to look at the hip joint angle, right? So in other words, the flexion. Okay. Okay. So most angles, they have some kind of zero reference point. Okay. So I'm going to draw a zero kind of offset from the horizontal axis, just so that you can better see it. Okay. So when we say a joint is at its 0-degree configuration, we call this the reference configuration. Okay. A lot of times it's, you know, not necessarily that the joint angle is 0 degrees. Sometimes it is, depending on how the joint is. But a lot of times, you know, remember we talked very early in the class that, you know, when you're kind of just standing up straight and you're kind of just relaxed, we call that the reference configuration. And so all angles are kind of measured relative to this reference. Okay. Okay. So the hip flexion angle as a function of time kind of goes something like this. Okay. All right, so first it kind of rises up. Okay. So this is kind of during the swing, or excuse me, this is during the stance phase when your knee is kind of or your foot is on the ground. Okay. There's going to be a period where it goes into extension. Okay. At a certain point right here, the toe is going to come off. So right here is toe off. Okay. And then it kind of goes like that, and then it kind of just repeats from there. Okay. All right, so the top part of the graph, is when the knee or the hip joint is in flexion. Okay. And the bottom part of the graph is when the hip joint is in extension. Okay. And remember, that's all relative to kind of the reference configuration. Okay. Let's look at another joint. So another joint that we have here is the knee joint. Okay, so this is going to be the knee flexion curve. Okay. So once again, horizontal axis will be time. Vertical axis will be knee joint angle. Okay. So the knee is interesting. So the knee, you know, very rarely do we say that the knee actually goes in extension, because the reference position for the knee is kind of when the knee is fully extended, right? So when you're kind of standing up straight, your knee is fully extended, that's the reference, okay? So when you look at a knee kind of a flexion graph, you know, everything is kind of in extension, okay? Or excuse me, in flexion. Okay, and so the graph kind of looks like this. And so you have kind of minor flexion during the stance phase. Okay, so during the stance phase, your knee kind of is bending a little bit, but then right when the toe comes off, right? Remember, there's one kind of important part where when your foot is in swing, right? Your knee needs to kind of tuck itself in order for your leg to kind of swing forward. Okay? And so the knee flexion angle actually goes up quite a bit during Okay. So the details of these specific graphs, are not that important, or at least not for you to know right now. Just kind of the point of this section is just to introduce the idea of kinematics. And you'll be seeing kind of graphs like this, in the future. Okay. So a lot of times, when you are asked to kind of find the kinematics of a particular joint, what you're interested in is basically a graph like this. Okay. So oftentimes we want to obtain information about how the joint angles at the joints change with time throughout the motion. Okay. And the way that we often do this, at least in practice, is through motion capture. So that'll be in a couple weeks. Unfortunately, I don't have any motion capture setups for us to try in the class. Instead we're gonna run through the calculations in terms of how do you go from motion capture data to data like this, which you can use for biomechanical analysis. Okay. All right, any questions on this? Okay. All right, so that's about it with walking. Let's go ahead and jump to running now. Okay. So running, hopefully needs no introduction. Running is kind of the motion that you go through when you need to move quickly, right? So when you need to, move your body from one location to another, you need to do it quickly. People often do it by running. Okay. So running, it's a little bit harder to quantify relative to walking because the speed and the speed at which you run really depends on how much energy that you can exert during the running. Okay. Okay. And so when you're running, you're going to exert a lot more energy, but that's kind of obvious, right? So if you've ever run before, that's you feel it, right? Okay. So running has a few different stages compared to walking. Okay. And so once again, I'm going to go through just one particular leg. Okay. So we're going to start our gait cycle or running gait cycle right when your foot touches the ground, right? So the first thing we have is foot contact. Okay. And so if I were to kind of draw this, it would look kind of something like this. Okay. And so your foot is contacting the ground. Okay. So your foot stays in contact with the ground for about 35% of the gait cycle. Okay. The next stage that happens is toe off. Okay. And so eventually, you're on your foot and then you kind of push off it and then your toe comes off the ground. Okay. And so that kind of looks something like this. Okay. So the toe off initiates what's called the swing phase, right? And so, the stance phase and swing phase, those have the same terms as the walking gait. Okay. So when your foot is not in contact with the ground, this starts the swing phase. Okay. And unlike in walking, right, your one particular leg is going to spend the majority of time in the air when you're running. Okay. So it's about 65% of the gait cycle. Okay. All right. So while your knee is or while your leg is in the swing phase, there's a portion which we call peak knee flexion. Okay. So that's the portion of the phase where your knee is basically just tucked in as much as possible. Okay. Okay. A little bit exaggerated there, but but you get the point. Okay. Okay. And then your leg kind of swings forward, and then you make another foot contact event. Okay. And so we kind of come back up to the top. We come back to foot contact. Okay. So the main difference here is kind of the different proportions of the stance phase versus the swing phase. Okay. So when you're running, the swing phase is a lot more prominent. Okay. In fact, the fact that each of your legs spends more time in the air means that there's a portion of the gait cycle where neither of your legs are on the ground. Okay. Okay. And that portion of the gait cycle where both your legs are in their swing phase, we call that flight. Okay. So that takes place for about 15% of the total gait cycle. Okay. Okay. And of course, all the terms that we use to describe the walking gait cycle, things like the step length, the stride length, the cadence, the frequency, stride frequency, all those are the same here. Okay. The only difference is that, for most people, how fast you run really depends on how much energy that you put in. Because, running can be used to describe something like a light jog all the way to kind of a full-on sprint. And so both of those have similar kind of biomechanics in terms of, in terms of the motion and what it looks like. But of course, one goes faster than the other one because you're exerting more energy in sprinting versus jogging. Okay. All right. Any questions on this? Okay. All right. So let's look at the energetics of the running gait cycle. Okay. So we can do kind of a similar analysis that to what we did during walking, right? So remember during walking, we looked at some typical force plate data. And so, the forces that the ground pushes back on the body while it's walking. So we can do the same thing for running, okay? I'm going to skip a little bit of kind of the introduction. So, I'm just going to jump straight to the kinetic and potential energy graph just because that's the one that's kind of the most interesting, okay? Okay, so if we draw our graph here, so on the horizontal axis, again, we have time. Okay, on the vertical axis, we have energy. Okay. So just kind of very similar to walking, right? The potential energy is going to go up and down as the person, takes steps and goes through the gait cycle. Okay. So in red right here, this will be kind of the potential energy. Okay. So as you kind of take steps when you're running, your center of mass is going to kind of go up and down. Okay. So depending on whether you're kind of stance phase, swing phase, where you are in the cycle. Okay. Now, what we saw with walking was that, this was out of phase with the kinetic energy, right? And so, when one was up, the other was down. And that kind of led us to our ballistic walking model. Okay. Running is actually very interesting. So running, if you actually plot it out, what you'll see is that the kinetic energy is actually very much in line or in phase with the potential energy. Okay. And so it looks kind of like a subtle difference, but it actually kind of makes sense when you think about kind of the biomechanics of running. Okay. Okay. And so when these two graphs were out of phase, what we basically said was that, kinetic and potential energy were all just kind of trading off with each other, right? There was no really, input of additional energy. So what we said was that walking was mostly passive, okay? When these two are in phase, we don't really have an equivalent exchange anymore because both are going up and down at the same times. Okay. Instead, what's happening is that, your muscles are kind of actively exerting and putting a lot of energy into the system in order to kind of propel your body forward. Okay. So kind of a very kind of quick explanation of what's happening is that during the stance phase, okay, so when your foot is on the ground, what happens during that phase is that your muscles kind of, are kind of preparing to kind of lift off. I guess that's kind of the best way to describe it. Okay. So during the stance phase, your muscles and tendons kind of temporarily kind of store energy in itself, kind of almost like a spring. Okay. Okay. And so when the person is kind of, you know, in their stance phase, okay. And so if we look at this leg right here, right, you can see that it's in stance, it's on the ground, right? One analogy that we can make here is that that's kind of similar to kind of compressing a spring, right? Okay. Right, so during the stance phase, you know, you're kind of, you know, your body, your center of mass kind of goes down. And what's happening there is that, you know, you're kind of building up potential energy within your muscles, right? Your gravitational potential energy may be going down, but your muscles are preparing to kind of, you know, do a kind of big burst of energy there, okay? And then during the swing phase, or I say right when the stance phase ends, so right when the swing phase begins, okay? So when the swing phase begins, so that's after the, so what's happening there is that your muscles are kind of exerting a lot. It's pushing off the ground. Okay. And all that kind of elastic energy kind of comes out, and that's kind of what pushes your body forward. Okay. All right, so the model here is quite different. So no longer do we have kind of a pendulum that's approximating this. So now we're using this kind of spring analogy, kind of actively compressing the spring and then releasing that spring to kind of, you know, give us a burst of kinetic energy. Okay, compressing the spring, releasing, compressing and releasing. Okay, so this spring, right? This spring here kind of gives us that's kind of our simplified model. So that's kind of our rudimentary kind of model for running, okay? As opposed to the pendulum, the actively compressing and releasing a spring is kind of that's kind of the first analogy that people typically use. Okay. And interestingly, you know, people have kind of used that kind of spring analogy where, you know, people have, you know, of course, you know, just like the pendulum, people have tried to use this model to kind of, you know, to mimic the motion of running or to better understand it. So people have actually kind of made pogo robots that are used to kind of model kind of the motion of running. So it's a robot that basically has a spring and it can kind of rotate around a pivot, right? And then it kind of, you know, pushes itself forward by, you know, by jumping and then compressing and then jumping and then compressing, right? Kind of using the very similar kinematics to run. All right, any questions on the kind of this model here, just kind of the energetics of running? Okay. All right. One really interesting actually use for this is in the design of running tracks. Okay. So this is just kind of a very interesting kind of example. So it's a little bit of a sidetrack, but I think it's kind of cool to kind of see, you know, kind of the endpoint of kind of all these models and all these things that we're discussing. Okay. Okay. So for a very long time, you know, sports, people who design sports tracks and sports shoes, they had a really hard time designing the perfect track. Right? Because before, right, when you think of, what is a well-designed track is, the people always thought that, the best track is the one that makes people run the fastest. And so conventional wisdom was that, let's make the track as hard as possible to kind of help people kind of run faster. Okay. So kind of the thought process behind this was that, if you've ever tried running in sand or have you tried running in any kind of soft material, it's really hard because, you step down, your foot kind of takes some time to sink into the ground. And then that time, it takes you longer to kind of push off there and it makes you run slower, right? And so the opposite of sand is concrete, right? And so that the idea is that, if you make your track surface as hard as possible, that's going to, minimize the amount of time your foot stays in contact with the ground. You have a lot of kind of, conservation momentum. You have kind of a lot of bounce back as well. And so the idea was that, if you make your track surfaces really hard, then runners would just go faster and get better times and things like that. Okay. And in an era where, where things like, the Olympics and Guinness Book of World Records, was becoming a thing, people were trying all different things to try to get the fastest times possible. Okay. Now, we know a lot better now. So we know that if you run on a really hard surface, you're just kind of asking just to kind of, mess up your knees and mess up your shins and ankles. Okay. Okay. So now we know, don't leave this classroom and go run on the concrete as fast as you can, right? Because, if you do that enough, uh, running on a hard surface will put a lot of stress on your bones and your joints. So, you typically don't want to do that. Okay. And if you go to any running track nowadays, what you'll notice is that the track is always made of this kind of spongy kind of material, right? And so if you kind of walk on the track, it kind of feels a little bit nice to walk on because, it feels kind of soft. And so not only does that surface there meant to prevent injuries, you could actually get a faster running time from that as well. Okay. And the whole idea behind, using a soft surface to improve running times comes from the fact that, when you're running, your leg kind of acts like a spring, right? Right. And so the thing about a spring and the thing with kind of any kind of elastic property is that a spring will kind of naturally vibrate or naturally kind of oscillate at its own natural frequency. Okay. So, you may have experienced this as well. So if you've ever taken a very strong spring and you kind of, push it in, right? It's going to want to kind of release itself. But, if you notice, there's kind of a natural speed at which kind of the spring will uncoil itself, right? So if you kind of just leave it to its own devices, there's a natural speed in which it kind of does that, okay? Okay. And so once scientists kind of, start to notice this, they thought, can we leverage this, can we leverage this analogy? Can we leverage this model to better design our tracks? Okay. Okay. So let me kind of draw you, let me draw a figure. Okay. And so if we were kind of to, let's say that this line down here is the hard ground. So, underneath the track, you may have something like concrete. Okay. You need to give it a stable foundation. But the track itself, might be kind of a layer of kind of springy material that's on top of the concrete. Okay. And if the track is made of this kind of springy material, you can kind of model its behavior like a spring as well. Okay. Right. And so it's almost kind of like you're standing on a platform that's supported by a bunch of tiny little springs. Okay. So this spring right here, we can quantify its behavior through its natural spring constant, right? So we say that the track has its own spring constant, K track, okay? When a foot makes contact with the ground, right? Right, so let's say this is kind of right in the middle of the stance phase. The foot itself, as we just saw, also kind of acts like a spring when it's running, right? Okay. So when the foot makes contact with the ground, the leg itself also kind of acts like a spring. So we have kind of two springs in series here. Okay. Okay. Now, if you have two springs in series, right, their exact behavior is kind of the summation or kind of a combination of both of these springs together, right? And the goal, right, the goal here is to try to minimize the amount of time that the foot is in contact with the ground, right? So when the foot comes in contact with the ground during the stance phase, the foot is going to push downwards, okay? And so it's going to compress both springs. Okay, so both springs are going to get compressed. Both springs are going to be compressed during the stance phase. And the objective here is to try to minimize the amount of time that the foot stays in contact with the ground, right? So we want to kind of maximize the amount or maximize the speed at which, the kickback kind of occurs. Okay. And so what scientists found, and so through a bunch of experiments, right? And so they ran experiments with, varying track stiffnesses, okay? Because the leg stiffness you can't really do anything about. That's the stiffness of the person's leg, right? And of course, there's variations of that, between different people. But the one variable here, the one variable that we have control over is the springiness of the track, okay? And what scientists found is that, actually, if you want to maximize running speed, the goal is not to set the springiness of the track to be as hard as possible, okay? So very hard surfaces, okay? Very hard surfaces are those where the spring constant is extremely high. Okay. So what they found was that very hard surfaces actually underperform situations with a softer springiness. Okay. And so what scientists has found is that, if K track or the springiness of the track is around, anywhere between 2 to 4 times the stiffness of the person's leg. Okay. And so if you have a track stiffness that's, roughly about 2 to 4 times more stiff than the human leg, this is what leads to best optimal performance. Okay. So that's why, when you step onto a running track, it's it feels kind of soft. Not only does it have the benefit of, making sure that our sprinters and stuff and long jumpers don't hurt themselves, but it also gives them a little bit better performance as well. Okay. Because what tends to happen is that when the surface is too stiff or when it's too hard, you have a spring that's kind of trying to push down. You have kind of a relatively soft spring trying to push down on a really hard spring. And so that kind of limits how quickly the soft spring can contract. But if you have two springs that are in similar thickness, they both kind of contract at the same rate, and then they both release at the same rate as well. Okay, that's kind of a very kind of in a nutshell, kind of what scientists have found through this experiment. Okay. So yeah, so I mean, not a, I know we didn't really talk too much specifics here, but this is kind of a really cool application of this, of, taking a model, which, again, doesn't explain everything that has to do with running biomechanics, but, was actually used in a really, really useful way. Okay. And these are the kinds of, analyses, and these are the kinds of, projects that I think are really interesting, really cool. So kind of using biomechanics in a really creative way, to kind of really help a lot of people. All right, any questions on this? Okay. All right, so last thing I want to talk about before I give your exams back is the transition between running and walking. Okay. So the transition between walking and running is called gait transition. Okay. All right. So kind of the intuition that people have is that, when you go from walking to running is kind of a very smooth transition, right? And so, typically when people start running, it usually occurs when they start to kind of quicken their pace. Okay? So let me start by saying that, compared to walking, running has a much higher step frequency. Okay. And so you would think that, if you want to start running, you start walking fast enough, right? You increase your cadence, you increase your frequency enough so that, you no longer have the double support pace. Okay. But that's actually not the case. Okay? So the transition from walking to running is actually a little bit more abrupt. Okay. And the most important thing is that, or the most important reason is that the natural biomechanics of both motions are actually quite different. Okay. And so when you're locked into a particular motion where you have to have a double support, right? There's a very comfortable speed at which that occurs. Okay. Likewise, if you're into a certain motion where you have to have a certain flight phase, there's a certain speed in which that feels comfortable. Okay. So kind of the upshot of this is that if you try to kind of speed up the walking gait, so having the walking gait, or I'd say executing the walking gait, at high speeds is not very efficient for the body, right? And so kind of as you kind of increase the speed, your body is going to need to exert more energy to kind of keep up that speed. But if you want to maintain that motion where, you have kind of at least 1 foot on the ground all the time, that's really kind of uncomfortable to do at high speeds. Okay. If you've ever had the chance to watch, Olympic speed walking, you'll see that those people look very uncomfortable because it's very hard. And if you kind of ask my opinion, it kind of looks like most competitive speed walkers now are all cheating because they all kind of look like they're just running, and they're just kind of trying to call it walking for the sake of competition. Okay. Similarly, for a the running gait, that's really kind of difficult to do at low speeds, right? And so if you're kind of, trying to run at low speeds, you're basically just kind of hopping from one spot to the next. And that's also not very comfortable to do. Okay. So we didn't talk too much about it, but whenever you're in a particular gait, right, your joint motions and your body segments are kind of locked into a certain pattern, right? And so when you're running, your knee's going to flex more. When you're walking, you're going to have more action from your hip, and so on and so forth. Okay. And so there's kind of a natural speed that people walk at and a natural speed that people run at, that kind of maximizes energy efficiency. Okay. And so very rarely, if you see someone that needs to get to a place in a hurry, very rarely do you see them kind of, walk quickly at a constant speed. Okay. So actually the more, energy efficient way to do it is to do a combination of walking and running. So you walk at a comfortable speed for a certain time, then you run for a speed at a certain time. Okay. Okay. And you could try it, right? And so, let's say, maybe you're walking to your car at the end of the day, right? Try speed walking the entire walk from the classroom to the parking lot, and you'll see it's not easy to do. And so if you need to get to your car in a hurry, the best thing to do would be either just to run the entire way, or maybe you're not in that much of a hurry. So you maybe run half the way and then you walk half the way, or you run for a quarter, walk for a quarter, run for a quarter, walk for a quarter, right? You don't, it's very hard to kind of maintain kind of an intermediate speed. Okay. And so if you're wondering kind of what's the most comfortable speeds for most people, so walking speeds, kind of a comfortable walking speed is about 1.5 meters per second. Okay. It's a little bit higher than kind of what we talked about last time, but we're kind of assuming that you're in a hurry. So 1.5 is the kind of the max speed that you can walk and still kind of maintain, comfort. Okay. And so for running speed, for most people, it's about 4.0 meters per second. Okay. Now, of course, it is possible to run at greater speeds than 4.0 meters per second. So if you really just kind of, just haul ass, you just kind of sprint, it's possible to go. But then, in terms of what's comfortable with that particular gait, 4 meters per second is kind of about the average for most people. Okay. All right. Any final questions on this? Okay. All right. So I have your exams up here, so you guys can come pick it up. If you're on Zoom, I'll bring the exams again on Monday, so you can pick it up then. But or you can come to my office to pick it up. So I'll put it in 2 files. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys next week. Was that it? Oh yeah, no, it's great. Yeah.
This is more for my senior design project. We're designing something to help somebody get in and out of the Pirates of the Caribbean on Disneyland.
Cool.
If you were to suggest the easiest way for someone who is physically disabled but mobile, like they have control of all of their limbs.
Yeah.
To get up from a slightly inclined position, would you suggest having 2 handrails on each side to get up, or 1 handrail to pull up?
I think
one is a lot easier to climb than the other, but like I was thinking, does that even help, or like? They're not, the seats aren't on a 90-degree angle, they're actually like this.
Yeah.
With water, but it makes it hard for people to sit up because there's not handrails.
I think personally, I think having it above would feel better, just because you have something kind of anchoring above you. Because what happens kind of when you're kind of like in this, is that you feel a bit more unstable, I guess.
Yeah.
And so because think of the situation where it's like, you're trying to pull yourself up and you need to kind of adjust something. You feel a lot more stable hanging on with one hand up here, just because it's easier to kind of centralize it. But if you're kind of on this, you can't really just kind of lean on one arm.
Okay. That's what I thought too. And then I asked my grandma, because she's mobile.
Yeah.
She can only walk for so long.
Yeah.
And I was like, if I had to get up, so we were actually sitting in a restaurant and it was like a little incline. Like,
Yeah.
to get up in here, what would be the easiest way? She's like, oh, I just want 2 handrails. And I was like, okay, that's one person's opinion. And I was like,
Everyone's gonna have different preferences too.
yeah.
So.
I don't know what the word. I was like, oh no, please don't tell me that's like actually the right way.
Well, it's different opinions, right? And then,
Yeah.
when you're designing for a general audience, most people are gonna have opinions one way or the other.
Okay.
Because I'm thinking like when my grandma gets into a car, like she always holds like the thing. Yeah.
That's what I would think, is if you're like kind of sitting back and they're also not 90-degree. You're kind of sitting back, it would be easier to drive something above you.
Yeah.
Which we can hook onto the back of the second chair, because
Yeah.
they're like in rows. But I was like, if we take handrails here, like That would never work.
I think
So-
the thing is that when you're reaching up, I think some people have difficulty kind of reaching up too.
Yeah.
And it's a little bit more taxing on the body too, because it involves kind of more muscles, especially ones that they may not use all the time too. So I think the thing with like the ones on the side, that's probably what they're used to when they're just getting up from like a chair. And so that's something that kind of feels kind of comfortable for them. too.
Yeah. Done that a lot.
Exactly. Yeah,
But it would be like still, okay,
I think both are great options. It's just, but yeah, I think just getting more data from like actual old people is.
yeah, I know. That, I wrote the concept design and we're like, how are we gonna get in touch with like a lot of old people right now? But then I ended up going to my grandma's art show and I was like, guys, I found our old people. This is a 55 and older community.
Yeah, that's
Like,
perfect. That's perfect.
But, you would also say, I talked to my mom and then I was gonna talk to somebody who's in PT. Dude's not getting back to me. It's been 3 weeks, so I'm
Oh.
gonna ask you. Isn't it easier for people who have like knee or hip or ankle mobility issues to step with stairs versus ramps?
Yes, because
Okay.
stairs are flat.
That's, yeah, I figured that was a universally, it was an easier question, because it would be smaller steps with stairs is easier than just installing one.
Yeah,
ramp.
because if you have a ramp, you're getting more stability issues then too, because like if your foot is kind of slanted like this, it kind of puts your body kind of back or
Mhm.
puts it forward, and then you don't want them to fall forward or fall back too.
Okay. I wonder, can I ask you what their concept is?
Oh, yeah,
Is
sure.
that,
Yeah,
okay,
of course.
I didn't know if that would count under an NDA, and I was like.
Oh, well, if you guys signed an NDA, then maybe, ask your mentor if, at
Okay.
Disney, if it's, I'd be happy to look at it, but I don't want to get you guys in trouble either,
I
so.
honestly think it's Wu. He said great things about you last time. I was like,
Okay.
oh, I'm doing it.
Well, he's my friend, so
Yeah.
Yeah.
Like, oh, it's fine, I'll help you guys out. And I was like, okay, cool. I'm gonna.
yeah, I mean, I've talked to senior design groups before, but yeah, with the NDA stuff, I just don't want to get anybody.
Yeah, I'll ask Shannon on Friday because that's our class, but I was. Cause right now, like, we talked to the people at Disney and they really like stress the whole fact of. The idea that we needed to get